Okay, so now to section 3.7, which is about rates of change in the natural and social sciences. Rates of change in the natural and social sciences. Okay, so let's first discuss physics. In physics, if S of t equals the position function of a particle moving along a straight line, so S of t is displacement or position function of a particle moving along a straight line, then we define delta S over delta t. Remember, average rate of change. So this is average velocity because we're doing distance or position over time. So that's velocity or speed. So average velocity or average rate of change over a time period delta t. When we say delta S, that means change in position, and delta t obviously is change in time. It's like S of t plus h minus S of t over h. Basically, that's what it is. Okay, and v, the velocity, is the derivative of position with respect to time, which is the limit of delta S over delta t as the t goes to 0. Remember, this is what we used to call average rate of change. This is instantaneous rate of change. So this is instantaneous velocity. Instantaneous velocity. When we go to the limit, we get instantaneous. When we do average, we get when we do average, we get average rate of change. Okay. And A of t is called acceleration, which is the derivative of the velocity, which is the second derivative of the position function. We use v prime t. This is s double prime of t, which is the acceleration. Okay, acceleration or the second derivative. All right, let's go to number 10, page 235. And page 235. It says if a ball is thrown vertically with a velocity of 80 feet per second, then its height after t seconds is, so as its position after t seconds is 80t, that's the initial velocity, minus 16t squared. This is initial velocity, this is half the gravity. Gravity is negative 32 feet per second square. It's negative because gravity pulls downward. This is initial speed. So the position of the ball in terms of the time, what is the maximum height reached by the ball? What is the maximum height reached by the ball? So basically, if this is ground and throw a ball, it's gonna go up and it's gonna reach a maximum and then come back down to ground. So basically, that's why we have a parabola concave down. That's why we have a negative here. When it reaches a maximum height, whether you're going this way or you're going vertically up, that the speed there is 0. That's why it starts going down. So this is where v equals 0. Okay, so to find the velocity from the position, we just talked about that. Velocity is the derivative of the position. You want to do limit, you can do that, but you don't need to do limits anymore because now we have all these rules. So we can do the rules. So v is s prime of t. The derivative of 80t is 80 minus, that's 32t, equals 0, t equals 80 over 32, which is 2.5 seconds. They wanted the maximum height. We just found the time that will give us the maximum height. So to find the maximum height, we plug that in to s of 2.5, 80 minus 30 times 2.5, 80 minus 16 times 2.5 squared, which is 100 feet. So that's the maximum height reached by all is 100 feet. Okay, part B. What is the velocity of the rock when its height is 25 meters on its way up and on its way down? What's the velocity of the rock when its height is? So basically we want V when S is 20 meters per second. It's gonna go up, reach 20 meters, and then it's gonna come back down. Okay. So when S is 20 meters, I'm sorry, when it's 96 feet, I'm looking at the wrong one. Yeah, 96 feet, not 20 meters. Okay, 96 feet. Yeah, number 10B. So remember S of t equals 80t minus 16t squared. So let's find t when S is 96. T squared. So we're gonna set it equals 0 minus 96 and put it in descending order. Negative 16t squared plus 80t minus 96. Factor out negative 16 minus 5t plus 6 equals 0. This goes into, so t equals 3 seconds and t equals 2 seconds. Now we don't want the time, we want the velocity. Remember, the ball is going up. After 2 seconds, it's gonna reach 96 feet, and then coming back down in a second, it's gonna reach 96 feet. So that's why it's two times. This is going up and this is coming down. Okay, going up and then coming down. So v, the velocity at t equal 2 going up, v of 2, we have a formula for v to plug it in. V is 80 minus 32t, so 80 minus 32 times 2, so that's 16 feet per second. That's going up. Now at t equals 3, coming down, v of 3 is 80 minus 32 times 3, which is negative 16 feet per second, and it's negative because it's going downward. Okay. So number 6, page 235. Page 239. I'll just do part A. B is for your homework. Part B is similar, so your homework. Okay. It says graphs of position functions of two particles are shown. Well, we'll just look at A. Where t is measured in seconds. When is the velocity of each particle positive? When is it negative? When is each particle speeding up? When is it slowing down? That's a very good question. Okay, looking at the graph, so you need to be looking at this graph that I'm looking at. Let me see if I can zoom in. Okay, so we're looking at 6A right here. This is the one. Okay. So if you look between If you look between 0 and 1, look between 0 and 1. This is the position function, so this velocity is the derivative, which means slope of the tangent line. Between 0 and 1, the slope is positive, the tangent line has a positive slope. Then between 1 and 2, it has a negative slope. And then between actually 1 and 3, it has a negative slope. Between 3 and 4, it has a positive slope. Okay? Now, so they know when is the velocity positive? It's positive between 0 and 1, and then 3 and 4. Between 0 and 1, and 3 and 4. Okay? That's when the velocity is positive. When is it negative? Between 1 and 2, between 1 and 3. Okay, it's negative between 1 tangent line. When is each particle speeding up? When is it slowing down? Well, in order to figure out when it's speeding up or slowing down, we're going to look at velocity and acceleration. When they have the same sign, like velocity and acceleration are positive, then it's speeding up. When velocity and acceleration are negative, then they're speeding up. When they have opposite signs, velocity and acceleration, one is negative, one is positive, it's slowing down. Acceleration is second derivative, so this has something to do with concavity. Concave down meaning acceleration is negative, concave up meaning acceleration is positive. So between 0 and 2, acceleration is negative because it's concave down. Between 2 and 4, acceleration is positive because it's concave up. So I'm going to write all this down. Okay, so between 0 and 1, if t is between 0 and 1, then we got two things to look at. Velocity is positive because the tangent line has positive slope, and acceleration is negative because it's concave down, so it's slowing down. Now between 1 and 2, velocity is negative because the tangent line has negative slope, and acceleration is negative because the graph is concave down, so it's speeding up. If t is between 2 and 3, velocity is negative because it has slope negative, and then a is positive, it is concave up, so it's slowing down. And between 3 and 4, velocity is still positive, but acceleration is also positive, so it's speeding up. Okay, that's how we know. Now to number 18, page 235. Page 235. The volume of a growing spherical cell is, so volume of a sphere, as we know, it's 4/3 pi r cubed, where the radius is measured in micrometers. 1 micrometer is 10 to the negative 6 meters. Okay, that's the micrometer. Find the average rate of change of V with respect to R when R changes from, so I'll just do part 1. We want the average rate change of V with respect to R when R changes from 5 to 8 micrometers. 5 to 8 micrometers. So we want to do V of 8 basically minus V of 5 over 8 minus 5, or delta V over delta R. That's what we're doing. So we'll just put the numbers in there. 4/3 pi 8 cubed minus 4/3 pi 5 cubed. over 8 minus 5 is 3. If you do the math, it's roughly 540 micrometers square. Why square? Because on top you have cube, micrometers cube, it's a volume, and this is micrometers, so you get micrometers square. Okay, that's part A. Part B. Find the instantaneous rate of change. So when say instantaneous, that means we're going to find v prime of r or dv by dr. That means we're going to the limit, okay? But we don't have to do limits because we have the formula. V is 4 over 3 pi r cubed. So when I do dv by dr, you find the derivative. R is the variable, these are constants, so we leave the constant out. Derivative of r cubed is 3r squared. So it's 4 pi r squared. Show that the rate of change of the volume of a sphere with respect to its radius is equal to its surface area. Explain geometrically why this result is true. Argue by analogy of exercise 15c. You can argue with 15c. You can see this is the surface area of the sphere. That's exactly what the formula says, okay? And if you do the math, it's 4 pi times 5 squared, which is roughly 314 micrometers. Okay, that's it for number 6 and 18. Then we're going to do next number 22. Page 235. Okay, Newton's law of gravitation says that the magnitude F of the force exerted by a body of mass m on a body of mass big M is F equals G little m big M over r squared, where G is the gravitational constant. G is the gravitational constant. R is the distance between the bodies. And remember, little m is the mass of a body exerted on big M, which is the mass of the body that's getting exerted on. Okay, find df by dr and explain its meaning. What does the minus sign indicate? So if you find df by g, df by dr, r is the variable. So to do that, we all these are constants, g, m, big M, and we're going to write r to the negative 2, so it's negative 2 g, m, r to the negative 2 minus 1, which is negative 2 g, m over r cubed. So this is what this is. This is instantaneous rate of change of the force relative to r. R is the distance between the two bodies, relative to the distance between the two bodies. Since this is negative, that means the force exerted by little m on big M is decreasing, okay? This is negative, means that the force exerted by little m on big M is decreasing, okay, because the rate of change is negative, so that force is decreasing. Part B, suppose it's known that the earth acts an object with a force that decreases at a rate of 2 newtons per kilometer. So df by dr, since it's decreasing, so it's negative 2 newtons, right? It's decreasing, so it's negative, although they don't say it's negative, but decreasing means it's negative. When R is 20,000 kilometers, the distance between the two bodies, how fast does this force change when R is 1,000 kilometers? So how fast does this force change when R is 10,000? So if you get the bodies half as away as before, it was 20,000, bring it down to 10,000. How fast does this force change? What's dF by dr? So we're gonna find dF by dr when R is 10,000. So to find dF by dr, we need two things. We need this quantity, gravitational constant, the mass of the exerted body over the the body that getting exerted onto, and R. So we have R, but we need this quantity. To find this quantity, we're going to use that -2 when R is 20,000. So dF by dr equals -2 gmm over R cubed. When R is 20,000 and dF by dr is -2, -2 equals -2 gmm over 20,000 cubed. So gmm equals 20,000 cubed, because these cancel out and you cross multiply. So we take this and put it in there. Okay, and R now is 10,000. dF by dr is -2 20,000 cubed over 10,000 cubed, which is -16 newtons per kilometer. So that force is decreasing at the rate of 16 newtons per kilometer. Okay. Next, I want to see. So we saw some physics applications, and I showed you more than I could do in class because I have all the time now. Now economics applications. To do economics, we're gonna go over the formula that we're gonna use. So we're gonna let C of x, this is all in the notes, of course, you don't have to write it down. It's the total cost of producing x units. So if you're producing batteries, C of 100 is the total cost of producing 100 batteries. So if the number of items produced is increased from, say, x1 to x2, then delta C, which is the cost of that increase, the difference in the cost of that increase in items, which is called additional cost, right? Because you were producing at C of x1, now you're producing at C of x2, so that's additional cost. And delta C over the x, which is the change in cost over the change in items, or you can write as C of x plus delta x minus C of x over delta x. You can use this notation. It's the average rate of change as we know it of cost, and then C prime of x, which is the instantaneous rate of change, which is limit, which is calculus now, algebra to calculus, delta C over delta x. This is what we call marginal cost. So I'm sure you've read or heard about marginal cost. That's exactly what it is. It's the instantaneous rate of change of the cost. By finding the derivative of the cost, we get what we call the marginal cost. And then C prime of n is roughly C of n plus 1 minus C of n. What this means, it means the marginal cost of producing n units is roughly the cost of producing one more unit. Because you are at n, then you produce n plus 1. So when they say what's roughly the marginal cost of reducing n units, you find the difference between the cost of reducing n plus 1 and n, which is the cost of reducing an additional unit basically. And that's rough estimate, okay? That is a rough estimate. And if you wanna know where this came from, remember C prime of n is, C prime of n is C of the change in cost, so it's the limit as C of n plus delta n minus C of n over delta n. So basically if delta n is 1, so C of n plus 1 minus C of n over n plus 1 minus n, which is roughly C of n plus 1 minus C of n, roughly, without the limit, just so you can reason that. So when they say find an estimate for the marginal cost, you find the difference between C of n plus 1 and C of n, which is the cost of producing one additional unit. Let's see an example. 34 from page 238. 34 from page 238. It says the cost function for a certain commodity is C of Q is 84 plus 0.16 Q minus 0.0006 Q square plus 0.00000 Q. Part A, find and interpret C prime of 100. To do C prime of 100, we want to do C prime at any Q first, the derivative. We don't have to do limit. We have the formulas. That's 0.16 minus 2 times that is 0.0012 Q plus 3 times that 0.00009 Q square. So C prime of 100 is, if you plug 100 in there, it's 0.00009 times 100 square, which comes to 0.13. Remember, this is the marginal cost, which is roughly the cost of producing the 101st term, right? Remember what we said? It's the cost of reducing one more unit. So if you're doing C prime of 100, it's roughly C of 101 minus C of 100, which is the cost of reducing one more, which is the 101st unit. Okay, so this is roughly, which is roughly the cost of producing the 101st unit, having produced 100 units. So it's also the rate at which the cost is increasing when the 100th term is produced. That's exactly the cost of producing the 101st unit. Is part B. Compare C prime of 100, cost of producing 101 units. So what's C of 101 if you do that? 84 plus 0.16 101 minus 0.0006 times 101 square plus 0.00003 times 101 cubed. Put that in your calculator, you get 97.3. And what was C prime? And what was C of 100? So C100 is 97. So C of 101 minus C of 100, which is roughly 97.3, 13 minus 97, which is 0.13. So this is the cost of reducing the 101st unit compared to P prime of 100. It's exactly the same. Okay, it's exactly the same. So that's a very good estimate, by the way. And that ends the long section.